So let
I'll
us
just begin.
welcome Lance Williams, who will be presenting increased complexity and fitness of artificial cells that reproduce using spatially distributed asynchronous parallel processes. So without further ado, the stage is yours.
Okay, thank you very much. I'm from the University of New Mexico, and this is the latest in sort of a continuing line of research I've presented at A-Lifes over the year. Let's sort of define complexity first, because if our goal in open-ended evolution, for example, is to evolve organisms of increasing complexity, we should begin by defining it. One of the ways which we can define complexity is through Kolmogorov complexity, which is, you're all probably familiar with. It's the length of the shortest program that will print a given object or construct a given object. But this is not so useful for characterizing the complexity of organisms, because it's well known that for example, random objects or random strings have the highest Kolmogorov complexity. They are incompressible. So in an attempt to improve the defects or to come up with a more interesting notion of complexity, meaningful complexity that would be appropriate for characterizing, for example, the complexity of living things, Bennett came up with this idea called computational depth. And it differs in a subtle but interesting way from Kolmogorov complexity. Computational depth is not the length of the shortest program. It's the time required to construct or print an object given its shortest representation. And this has very nice properties. First of all, random strings have low computational depth. So it kind of corrects some, I think, some of the shortcomings of Kolmogorov complexity when applied to characterizing the complexity of living things in any case. Now, if we adopted Bennett's notion of computational depth as a form of complexity which we want to maximize over time, we get a kind of conundrum. And that's because one of the most common methods for characterizing an organism's fitness is its replication rate. Indeed, in like bacterial studies, sometimes replication rate is a proxy for fitness overall. But if we define complexity as things which take a long time to replicate, then there's going to be no chance that we can evolve more complex things when, by definition, these more complex things will be less fit. So how do we get out of this? Well, actually, before I talk about how we get out of this, I introduced this idea. So if you're all probably familiar with busy beaver Turing machines, and there's another concept called Quine, which is a self-replicating program or a program which prints itself. So in some sense, these highly complex things we're searching for are busy beaver quines. They take a long time to run. They have compact descriptions. But nevertheless, if they take a long time to run, they're going to be less fit, unless, and this is how we get out, we escape the trap we created for ourselves, unless we use parallel construction processes. And so if we define computational depth not to be the time required to replicate, but the time summed over all execution paths of so the time summed over all sub-processes, then we escape the trap. We can have organisms of increased complexity, and they can have greater fitness because they will decrease in shorter amounts of time, even though they're more complex. And so we can call these things parallel busy beaver quines. That's sort of what I thought this morning when I added that. Well, that's all very nice for sort of artificial systems. What about real systems? So this is a plot I made of data from the book Cell Biology by the Numbers, and it's fascinating. And I thought I was knowledgeable about biology, but until I dug deep into the numbers, I didn't discover things like this. And this is truly fascinating because what you see in the dashed line here, the dashed line is the dry mass of a cell without the water, and it's in femtograms, right? So this is an E. coli bacterium, and so we can see on the y-axis we have the mass of the cell in femtograms, and then on the x-axis we have tens of thousands of ribosomes. Okay, and then on the second y-axis coordinate, we have the replication time in minutes. And you see something astounding. Larger cells replicate faster. This is really interesting. I mean, larger cells have to bring together larger quantities of raw materials, use larger amounts of energy. They have to push or displace mass over larger distances. All this is accomplished in shorter time, in less time, in living cells. And so how is this possible? Well, I think this supports my thesis because it's only possible because of the massive overexpression of ribosomes. The cells with the shortest replication time, are both the largest and have the largest number of ribosomes, over as many as 70,000 in a single cell. Now, what's also funny about this, and I guess I'll talk about this a little bit later, is that there aren't 70,000 copies of the gene for encoding the ribosome. There are, in fact, there are only 7. So this is not just a massively parallel system, but it's in some sense a decompression quine. It's using amplification processes to massively to produce massive numbers of these ribosomes, overexpress these numbers of ribosomes relative to the representation of the genome itself. Okay, so this is interesting. So let's see what we can do with in an artificial system. And we can begin by looking at the von Neumann replicator. And I'm going to use von Neumann's notation here. I didn't make up this notation. This is from von Neumann himself. So a von Neumann replicator, according to von Neumann, is defined as follows. It's got these 5 pieces. A, B, C, and D are programs. And then phi of A plus B plus C plus D is a description or self-description. Okay. And the programs do different things. A translates, which is to say it produces programs from descriptions. B copies, which is to say it copies descriptions. C is control, and D is payload, the other things the cell needs to do. Now, for the moment, we're going to ignore C and D, and we're going to focus on translation and copying. Translation might be the thing that's done by ribosomes in the cell. Copying is the thing that would be done by DNA polymerases. There's no analog in this model to transcription. But what about parallelizing the von Neumann replicator? Well, let's look at the 2 sub-problems that the von Neumann replicator has to solve. It has to solve the translation problem, which is to say, producing the suite of programs from the self-description, and it's got to solve the copying problem. And well, unfortunately, we can't do these 2 things in parallel, especially if these elements are implemented, say, as in an artificial chemistry, and the representation is not spatially distributed like a nucleoid in a real cell, but is a single actor. Then there's a problem because both of these tasks, translation and copying, must use the description, and only one can use it at a time. And so we write that constraint like this: A/B, meaning the subproblems A, translation, and B, copying, cannot be performed at the same time. So we have to come up with a strategy, and there is a simple sequential strategy, obviously. We can translate and then copy. And of course, we could equally well just copy and then translate, but there's no parallelism here. This is a sequential strategy. In fact, it's essentially the strategy that von Neumann's replicator used itself. Can we create opportunities for parallelism? And how will we do that? Because this is not very parallelizable at the moment. Well, the easiest way to create opportunities, reduce contention for the description, is to split it up. Instead of being a nucleoid, a single large molecule, or excuse me, a single molecule is compact, and it's under the assumptions I made in the last slide, we divide it into 4 plasmids, 1 for each program. And this improves the situation dramatically. We now have 8 subproblems instead of 2, and I can call these things AX and BX. This is translation of each of the 4 plasmids, A, B, C, D, and this is copying of each of the 4 plasmids, A, B, C, D. And then we have constraints on simultaneous execution because the same plasmid cannot be translated and copied at the same time. And similarly, a single instance of the translation program cannot operate on 2 different plasmids at the same time. So these are constraints based upon single resources and access to single resources. And we can still solve this problem sequentially. And now we have 8 steps. And this looks like we've moved in the wrong direction. But remember, each of these steps is now 1/8 the size. So the overall number of operations performed in the replication is still the same. And I've shown one sequence here, and it's, of course, one of 8 factorial possible orderings. This is, we have many, the order of operations is very, very unconstrained in this concurrent system, but there's no parallelism yet. So how about parallel strategies? Well, we can, in fact, after splitting the self-description across the plasmids, distributing it, subject to those 2 constraints, we can come up with a parallel strategy. And I've used these vertical bars to indicate 2 sub-problems that can be solved in parallel. So here's a parallel strategy which only has 4 steps. And again, it's one of many, many possible parallel strategies. But this is one that's permissible based upon the constraints, and it results in a 2 times speed up relative to the sequential strategy and relative to the non-distributed genome. Okay, well, that's a pretty good start. Can we do better? Well, what we have to do is, I mentioned that the bacterium did not actually have 70,000 instances of the gene which encoded the ribosome. But as a simpler first step towards achieving parallelism in a self-replicator of this sort, we can simply increase the gene copy number. And I'm using, that's the term that geneticists use, copy number, when a gene is duplicated. So instead of having a single instance of the translate and copy programs and this translate and copy plasmids, we can have n instances now. Okay, and when we do that, let's look at the situation for n equals 2. Now we have 12 different sub-problems, and they're subject to the same constraints as before. But this new system, which has increased copy number, n equals 2, I mean, it's a very modest increase in the copy number. We've got 2 copies of the translation program and 2 copies of the copying program. It produces an 8/3 speed up relative to the sequential strategy, and that's a pretty nice speed up. That's greater than a factor of 2. Okay, so what we're going to do today is we're going to talk about an artificial cell that uses increased copy number of the programs that construct or synthesize its component parts to reproduce more slowly. And what we're going to do eventually is we're going to demonstrate cells that are significantly larger than other cells. And despite the fact that they're significantly larger, they reproduce faster, as do biological cells. So in order to do this experiment, broadly speaking, I do artificial chemistry. This is a review of artificial chemistry, in general. I do a very specific kind, which I'm going to talk about in a second. But an artificial chemistry is a formal system for construction of objects. That's all it is. We can call the elemental objects atoms. The objects are composed using rules. In typical artificial chemistries, the objects can be strings or graphs. But significantly, there's no connection between the objects and the rules. The rules are sort of immutable part of the universe or the physics, and the objects that are constructed according to these fixed set of rules. There's a different and more interesting kind of artificial chemistry. I call it a combinator chemistry. It's similar to what the York group calls automata chemistries, but it's also different. And I think the combinator chemistry, I think that's cooler, and it's more accurate also because this field, this notion of a combinator chemistry, actually, I think we can credit Fontana and Buss way back in the mid-90s for this idea. So I'm going to call it a combinator chemistry. And the atoms in the combinator chemistry are program fragments, and that's kind of the technical definition of a combinator. It's a fragment of a computer program, and the rules themselves, which govern the behavior of the system, they're made of combinators. So the important distinction between this kind of chemistry and a traditional artificial chemistry is that the rules themselves are constructible objects. And so not only can the organisms within the world evolve, but the rules themselves can evolve. Okay, and that's profoundly different than the conventional artificial chemistry, and that gives these systems a kind of semantic closure that's not possible with the other kinds of artificial chemistries. And I mentioned this term monads because I gave a tutorial last A-Life on functional programming, and monads are just an abstract data type for representing program fragments. And so this combinator chemistry makes extensive use of it. So I have a specific object-oriented combinator chemistry. It's the one I use in all my experiments. The actors are located on a 2D lattice. They're subject to diffusion. Computations progress when actors interact with other actors in their neighborhoods. There's conservation of mass. Actors are neither created nor destroyed. And it's an event-driven simulation using the Gillespie algorithm. Anybody who's really interested in how this works in detail should look at my journal paper from about 5 years ago in the journal Artificial Life, and all this is described in great detail. So what is an artificial cell? Well, an artificial cell needs two parts. It needs a way of reproducing its components, and then it needs a way to organize its components into mother and daughter cells. Let's talk about the first one first. So this is a very complicated slide. In some sense, it's just supposed to show you, give you an idea of the complexity of the system I'm talking about. But this shows this system I use for copying and translating programs and descriptions in the artificial cells I made. And it's actually a pipeline parallel process with 6 steps. And the input over here is a plasmid. There's a forward traversal of the plasmid, which produces 2 reversed copies. And then there's a reversed traversal of those copies with a simultaneous second copying action, which produces 3 copies of the plasmid in total. That leaves 2 surplus. One is the input again, 2 surplus, 1 is program and 1 is data. So this 6-step process does translation and copying in 6 steps. And you might wonder, well, why did I do it this way? Well, it was very easy to implement in the combinator chemistry that I designed, because all this stuff can be done with just very simple operations, pushing and popping of the combinators onto stacks and creating bonds. No need for internal pointers, no need for addressing. It's actually, this computation can be implemented with a very simple combinator interface. Okay, I'm not going to say very much more about copying and translation. Let's talk about the second problem, how to segregate or organize the duplicated components into mother and daughter, how to segregate the components from those of other cells. Well, all these computations take place on a discrete lattice. We can consider a relation on the lattice. A lattice relation is a relation that's on the vertices, which is restricted to the 4 cardinal directions. So this is a lattice relation. And then we can consider the connected components of the lattice relation. Now, these connected components can be the domains of 2 different artificial cells. And they wouldn't be very interesting if they didn't move, but we can actually create equations of motion, stochastic equations of motion for these connected components, and they can evolve in shape, and they can move just like living cells. This is all described in greater detail in the paper from I presented at Newcastle 2 years ago. But I call this representation a roving pile. And there's the stochastically evolving connected components of a lattice relation. And they form isolated domains that are capable of hosting private message passing computations, just the sort of kind of computations we can specify in the object-oriented combinator chemistry. The domains, the footprints of these piles, they evolve in shape and move, they grow and shrink. But moreover, there's internal diffusion within the domains themselves, and that drives the computation, because the computation in some sense is diffusion driven within these roving piles. As actors come into the neighborhoods of other actors which match their preconditions, computation progresses. So this shows you just the stochastic motion of 2 of these roving piles. And so you can see they look very lifelike. And so this is not a static thing at all. This is a very dynamic computation. So I did something, I improved the system I described in Newcastle 2 years ago, but in a pretty significant way in order to get the results I'm going to show you today. And that is, I introduced roving piles, not just this, which have multiple compartments. And I'm going to illustrate that with this slide, because this is a fairly simple slide to understand before I get into the more complex one. We can have a roving pile, which is an annulus. This is a topological ring. This is a hole here. So this is the connected component here. It's an O, right? But we can create a circular shape pile, And then we can perform a topological identification. And when we do that, what we get is a pile with two compartments. And we can call this one the cell and this one a vacuole. And then I can extend the combinator chemistry with two functions, two combinators, which can serve as an interface. And this division between vacuole and cell is selectively permeable. It will pass things in one direction in the give state and pass things in the other direction in the take state. And so it's very simple to produce programs which will import or export from this vacuole using this device. And so I wanted to show you that because this is the situation for representing membranes of cells which are capable of binary fission. So on the left here, I'm showing you a picture that's loosely inspired by real biology. This is a sphere. This is the mother cell. This is a second sphere. This is the daughter cell. This mother cell has got an opening at the bottom. The daughter cell's got an opening at the top. This is a disk, and it divides the mother and daughter cell volumes. I'm going to call that disk the septum, which is in fact what it's called in biology. Now, so this is a reasonable biological picture. If we add an additional opening, this becomes non-biological now. If we add an additional opening to the mother at the top and to the daughter at the bottom, then this topological complex, which is embedded in 3 space, as I show here, can be immersed in the plane like this. This whole object here can be flattened like this. And if you have good topological viewing skills, you can probably see how that's done. But here we have the daughter cell, here we have the mother cell, and here we have the septum. And this is no longer an embedding, so this is a many-to-one mapping from the topological complex to the lattice. But that's not a problem. I mean, all that is easily taken care of with a little bit of cleverness in the implementation. And now I introduce a new interface, which allows a mother cell to to export to the daughter, either directly, which is this, and vice versa. The daughter can send things back, or through the septum, because the mother can send things to the septum through this open combinator, or receive things from the septum using the closed combinator. And similarly, the daughter gets the same interface. It can interact with the septum. What's kind of cute about this whole thing is that the relative rate of diffusion between mother and daughter of actors in the export state depends upon the perimeter of the septum. The larger the perimeter, because everything is going through the septum in some sense, even in this state. So I can control the rate of diffusion between mother and daughter by controlling the area of the septum, and I can control the area of the septum using these open and closed combinators, which can shrink it or expand it. Okay, hopefully that makes a little bit of sense. Then the only other pieces of the puzzle for required for binary fission are I have to add 2 combinators, one that creates a bud, a daughter bud, and one that performs the actual destruction of the septum and results into two daughter cells, or the mother and daughter cells, excuse me. So the only point I want to make here is that the operation which creates the bud is an operation which can be performed in a local neighborhood of the lattice. It's a 3x3 Moore neighborhood, because the daughter cell initially is very small. So this is something that doesn't require any great complexity. It's a local operation in a neighborhood. And similarly, once the septum shrinks to a single site, it can be deleted with another operator, which again is local. So that leads to this, which is a sort of schematic picture of the artificial cell I'm talking about. Here we have the replication pipe, the synthesis pipeline in the mother. This is the synthesis pipeline for the daughter. This is the septum. Significantly, we have the 2 forward and backward traversals of the plasmid. And those are the B and E programs. And these are the ones which we're going to increase the copy number of in order to produce parallelism. And so these are the only ones which take substantial time. All these other C, D, F, and A are relatively quick. These B and E, they require time proportional to the length of the plasmid. So those are the ones we're going to increase the copy number of in this system. So so this is what this, and I show that here. Okay. So this is our experimental results. Over here we have over here we have the mass of the cell, and you can see as the copy number of the B and E programs is increased, the mass steadily increases. And this is the replication time in operations, and we can see that the number of operations, excuse me, this is not summed over all processes, but this is that's one of the uses of the Gillespie algorithm. It can literally tell you how much time things took. It doesn't care about the parallelism. So this is the actual replication time, even in operations. We can see it steadily goes down as the copy number increases. So this is one copy of the B&E programs, 2, 3, 4, 5, and 6. So it's finally asymptoting down here. There's a point of diminishing return in this system after about 5 copies of the B&E programs. Nevertheless, it's eerily similar to the slide I showed you 20 minutes ago, which shows that larger cells replicate more faster based upon increased numbers of ribosomes. Okay, I should point out this, sadly, this figure is wrong in the printed version of the proceedings. I screwed it up. It was a stupid version number problem, and I feel really bad. It's the most important slide in the whole talk, and it's wrong in the paper, but it's right here, and my personal webpage is going to have the corrected figure. So let's just conclude. You know, I believe that replication by spatially distributed asynchronous parallel process is absolutely indispensable to open-ended evolution. I really just don't, I believe in this definition of complexity that Bennett has suggested, and I don't believe there's any way to create more complex things defined in the way Bennett wants to define them apart from parallel processing.
We have.
I'm going to say 10 more seconds worth of stuff. There's very little prior research on this topic. I was surprised. I found almost no research on parallel self-replication. And I'll let you read the rest of the conclusion because I am out of time. And I'll stop here.
No, don't worry. We have 5 more minutes. That was just a warning that.
That was just the warning, not the cutoff.
5 minutes.
Okay,
I
will
enjoy them.
I will read the last 2 sentences because it will make me feel better. Yeah, there's very little prior research on this topic. I found a single paper on parallel self-replication, really, and that was done on a multiprocessor architecture, not a multi-computer architecture. And for reasons which are described in the paper, I don't think that's as interesting. So I really think this is a wide open field, parallel self-replication, and I think it's as I said, it's an essential part of the problem of open-ended evolution. So it's a little bit of a shame that this talk is happening concurrent with the workshop, because I think the people in that workshop would benefit from seeing this point made. But finally, a combinator chemistry was used to build complex artificial cells, and they reproduce in less time than simpler cells, just like biological cells. And that was accomplished by increasing the copy number of programs used by the cell to synthesize its component parts. So now I'll stop. Thank you.
Thank you so much, Lance. Thank you for the fascinating talk and for relating your results also to the complexity metrics, which is a fundamental A-Life topic. So let me give you a round of applause. And we have one question in the Q&A. I thought, would you like to answer, or maybe I will read it. It's going to be simpler. So do you have collaborators or colleagues working in an experimental confirmation of your findings?
Well, if you're thinking about biological confirmation, I mean, the results I showed for real cells are just from the textbook Cell Biology by the Numbers. So they're well-known results in the field. The experimental works on the artificial cells are done by me. I mean, I think that, I guess I don't completely understand the question. I don't have, there are no other persons using this combinator chemistry, although I'd love for people to use it. I'm going to release it as a software library. That's my plan to do so this year. Well,
thank you for the answer. If I dare to interpret, maybe Heitor could have meant if there are some biologists aggregating more experimental data, which you could compare to which you could compare the properties of the artificial simulations to see whether uh, they would correlate in other measures than the than the time of the reproductions and the mass.
I'll take this opportunity because you're interested in the biology. So I'll take this opportunity to say something about where I could make this simulation more realistic biologically, and therefore there would be more opportunity to do what you just asked. And that is, right now the system doesn't do any transcription. You know, we know that in the fundamental dogma that we take DNA to mRNA, and mRNA is translated into protein by ribosomes. It's that transcription phase which performs the massive amplification of the gene. You know, you can't really scale parallelism using by doing the trick I did with increasing copy number. To get the kind of massive parallelism that the cell uses, you need to have transcription. So there needs to be this extra step in the process. And once I do that, there'll probably be more things I can relate to the actual living cell, and then the question will be easier to answer.
I see. Thank you so much.